Chapter 28, Systems of Linear Equations. And in the previous chapter, 27, we learned how to write the equation for a line. And in 28, basically what we're going to look at are two equations of two lines. So a system is a set of two or more linear equations. It's pretty simple. Okay. And they're linear, and so they fit the format that we learned about in the previous chapter, the slope-intercept form. Okay. Now, a solution in the previous chapter was a x and y pair that satisfied the equation. In this chapter, having two equations, we want an x and y pair that satisfy both equations at the same time. Okay, and that's not changing the x and y. The numbers x and y that work for one also work for the other. And later we'll see what that works out to graphically. So in example 1, what we're doing is we have two lines, line 1 and line 2. They're both linear. Line 1 is in slope-intercept form. Line 2 is in the general linear equation format. And if you check the variables, you should see that we have powers of 1 for our variables x and y. So they are linear. Okay. Well, below we have a table, and we have 1, 2, 3 pairs of coordinates. An XY pair, an ordered pair. And we want to check each 3 of these ordered pairs with line 1 and line 2 and determine whether they fall on line 1, 2, both, or neither one of them. Alright, so for line 1, we simply put in the first ordered pair that we're going to test, -9, -6 for x and y. -9 is my x coordinate, -6 is my y coordinate. So here we go. Line 1 is y comes first, it's on the right, and that is a -6. Then we multiply the x, -9, by a -4, which is our slope of this line, and then we add 6 to that. So we simply want to check the right hand side and make sure it matches the left hand side. Okay, we end up with 36 plus 6, a 42. And that does not equal the -6 on the left. And so we can't check the line 1 off for this ordered pair, -9, -6. It is not a solution to line 2 or line 1. Okay, we're going to do line 2 same way, same ordered pair. And so we have 2 times x, which is a -9, plus 7 times y, which is a -6, equals -10. 2 times -9 is a -18. 7 times -6 is a -42. We just want to calculate the left and compare it to the right, see if they're equal. But in this case, they're not equal. You have a -60 and a -10. So this ordered pair satisfies neither one of them, not line 1 or 2. Alright, so we have a little more work to do. We have to repeat that same procedure with a new ordered pair. 1, 2. 2 is our y coordinate, and line 1 has the y on the left side of the equal sign, so we write 2 equals minus 4 times 1. 1 is our x coordinate, and we have a negative 4 times x on the right side, and we add 6 to that. Negative 4 plus 6 is 2, and it checks out. The left hand side does equal the right hand side, and so we can check line 1. What about line 2? Same ordered pair, different equation. We have a positive 1 and 2 for x and y. X is multiplied by 2. The y is multiplied by 7. We get 14. 2 plus 14 is 16. And the two sides do not equal. And so the only one that we can check on line or in this row for the coordinates 1, 2 is line 1. So we haven't found a solution to the system, an ordered pair that satisfies both line 1 and 2. Maybe this last ordered pair is our solution. Y is on the left, we have a negative 2. X is on the right, it's multiplied by a negative 4, and then we add 6. Negative 4 times 2 is a negative 8. If we add 6 to that, we get a negative 2, which does match the left hand side. So it's a solution to line 1, but we can't say that it's a solution to the system yet. It has to be a solution to line 2 also. And that's what we're about to test. So we simply take line 2. We have a 2 times x. Our x is a 2. We add 7 times a negative 2. And we write down the right hand side. This is the number that we want that to work out to be. So 2 times 2 is a 4. 7 times a negative 2 is a negative 14. And 4 minus 14 is a negative 10. So this ordered pair works for both line 1 and 2. And so we can check 1, 2, and both. Alright. Since this ordered pair is the solution to both line 1 and 2, it is the solution to the system of equations. And this is the way you typically see a system written. Okay, we have a large bracket, and then we have equation 1 and then equation 2. Okay. So for instance, we won't solve any of these, but we could have a system of 3 equations. Okay. For instance, y equals 2x plus 1, 3x minus 5y equals 7, and then a third equation. Okay. Maybe an x plus 4y equals 3. Alright. And so we set them on top of each other, and we just put a bracket off to the side. Okay, example 2, we now are given 2 equations, and they're written in the standard way that a system of equations is written in. We have the bracket, and so this is equation 1, and this is equation 2. We want to figure out which one of these ordered pairs is a solution to the system, not just one equation. So what we're going to do is we're going to test one. Probably the easiest equation to test is this one, because the x and y aren't multiplied by any other numbers. And if our ordered pair doesn't work for this one equation, then it cannot be a solution to the system. So we would check no automatically without even checking the other equation. Alright, so y is on the left, my y coordinate's 2, x is on the right, it's a 3, and these aren't equal. 3 plus 2 does not equal 2, so no. The ordered pair 3, 2 is not a solution to the system. If we test the next one, we have 0 for y, 5 for x, and then we add 2 to it on the right. And this isn't true. 0 does not equal 7. And so this ordered pair doesn't work for equation 1. So it cannot be a solution to the system. Okay, y with the third ordered pair is a negative 6. X is a negative 6, and then we add 2 to it. We get a negative 4. But that doesn't equal the left hand side. So negative 6 is also not a solution. Okay, our last ordered pair, negative 1, positive 1. We'll test this same equation. Y is a 1, a positive. X is a negative 1. It's the first number in the ordered pair. We add 2 to it, and we get a positive 1. 2 minus 1 is positive 1, and that matches the left-hand side. So negative 1, 1 checks out for the first equation. Okay, but we're not finished. We now have to go and check the second equation. And then, if it satisfies the second one, then we can call it a solution to the system. Okay, y is 1. Oh, I wrote the same equation down. We want to check the other one. 2x minus 3y equals negative 5. We plug in negative 1 for x. Y is a 1. 2 times negative 1 is a negative 2. And then we have a negative 3 times 1 is a minus 3. And negative 2 minus 3 is a negative 5. And so we finally found our solution in the list. It was the last one. Okay, so to actually determine whether an ordered pair is a solution to the system, you have to check each equation. Okay, so as I mentioned before, there's another way, which we haven't talked about the algebraic way yet, but there's two ways you could say to find the solution to a system. The previous page, we were just given an ordered pair and we simply wanted to check whether it was a solution or not. On this page, we want to actually find the solution. Alright, so what we're going to do is just graph each equation, and we learned how to do that already in chapter 27. The second equation, y equals 1/2 x minus 2. It's already set up for us to graph it. This is the easiest format in that we have already a point on the line, our y-intercept, it's negative 2. And then we have our slope, which is just the number alone in front of the x variable. It's the coefficient of the x. It doesn't include the x. So our slope, m, for this second equation is just the 1/2. It's our rise over run. Now the first equation we were given in general form. And there's not really anything that we can do with the numbers -3 and 1, or the 3, okay, in terms of just plotting points. So we want to rearrange it to where we have it in this slope-intercept form, and then we can actually use the coefficient and the constant. Well, y doesn't have a number in front of it, and so we just simply need to move this term with the x to the right side of the equation, and we have to do that by adding a 3x to both sides. The 3x term cancels on the left, and then we are left with a 3x plus 3. And so, like equation 2, we now have the slope, the 3 in front of the x, and we have the y-intercept, also a 3. You could say it's just a coincidence, but this is where equation 1 crosses the y-axis. Alright, so at this point we want to graph each line on this coordinate system here. The vertical axis is our y-axis, the horizontal one's our x. With the constant of the equation being 3 for the first one, we simply go up to 3, a positive 3 on the y-axis, and plot a point. And then we apply our slope. Rise over run for equation 1 would be a 3 over 1. So we want to go up 3 and then right 1. Alright, so if I go 1, 2, 3 up and then right 1, that would put me right there. And remember, for the slope, if you sort of come to the edge of the coordinate system, going in one direction, you can simply change the sign of this positive slope. So I could write this instead as a -3 over a -1. A -3 divided by a -1 is still a slope of 3. It's just the minus minus is the double negative rule, and so we can drop those and make it positive. But by putting a negative in front of the 3, we can now go down and to the left in the opposite direction, but still with the same slope. Down 3, left 1, and we land there. We only really need 2 points, but if you want it to be accurate, then it's probably a good idea to apply the slope several times so that you get plenty of points to draw your line with. So here we are. All of these points fall in a straight line. So we do just that. We draw a straight line through them and we put arrows on the ends. Now we graph our second line. The y-intercept is a -2. Our slope, in other words our rise over run, is a 1 over a 2. And with each being positive, it means we go up for the rise, and the run is positive, which means we go to the right. So up 1 and right 2, and we have to start with a point on the line, okay? And that was our y-intercept, -2. So we go up 1 and then right 2. Up 1, right 2. Up 1, right 2. And if we apply our slope in the opposite direction, then we can write this slope as a -1 over a -2. And so that would mean I go down 1 and left 2. And if I go down 1 and left 2, I intersect the other equation, the other line. So I'll connect all of my points with a straight line. And here we have the intersection. Of the two lines. This is actually the solution to the system. Okay. If we figure out these coordinates, let's see, what are one of the coordinates. If we start at the origin, we have to go 2 units to the left. That would give us a -2 for x, and then 3 units down, and so that would give us a -3 for the y coordinate. It's kind of sloppy, so I'll rewrite it. -3. If we were to take this ordered pair and enter those values in for x and y in either equation, then the left hand side would equal the right hand side. This ordered pair satisfies both equations. It's the solution to the system. So example 3 gives us, let's see, 3 more systems. And so we're looking for an intersection, but we're not always guaranteed to actually have 2 lines that intersect. We have to graph them first to figure that out. For A, this equation's already in the slope-intercept form, so this is my y-intercept, and -2 is my slope. So I plot y equal -1 on the y-axis, or I'm sorry, +1, right there. And then I simply apply my slope of -2 over 1, which means that I go down 2 and right 1. So this is down -2 and right +1. So down 2 and right 1 lands me right there. And so if I apply it several times, I'll have a pretty accurate line. Down 2 over 1. Down 2 over 1. And then I simply just go in the opposite direction. Over 1 up 2. Over 1 up 2. Alright. So it's definitely nice when the equations are given to us in the slope-intercept form. Just simply go ahead and graph the line. But the first one wasn't. So we need to do a bit of work on it. We have x plus 2y equals 5. We need to get the y by itself. That's what it means to put the equation in slope-intercept form. So we subtract x from both sides. Okay, we're left with a 2y on the left. The x's cancel, and then we can't combine 5 and negative x, so we write negative x plus 5. And to finally get the y by itself, we divide everything in the equation by 2, every term. 2's cancel, and so we're left with y equals negative 1 over 2x plus 5 halves. Alright, so if we go to 5 halves, which is about 2.5 on the y-axis, 1, 2, and then a half, we'll start our equation right here. And this is a little awkward to graph because we're going to start at a half mark instead of a whole mark on our coordinate system. The slope is a negative 1/2, and so that means we go down 1 and right 2. So if I go down 1 from 2.5, I land at 1.5, and then I go to the right 2 because I have a positive 2 on the bottom. I've already interpreted the negative as directing me downward for my rise, so I've used my negative. Now I go right 2, and I land right there. Okay. And so if we keep going to the right, we're never going to intersect the first equation that we sketched. So I'm going to go to the left, and to do that, I simply write my slope with the negative associated with the 2 on the bottom. So now my rise is up 1, and my run is left 2. So if I go up 1, I'm still at a half mark on the y-axis, but then I go left 1, 2, and I land right about there. And you can see that this other point that we graphed for the first equation falls right in line with these other 2 points that we plotted for the second equation. So if I connect all of my dots, we read the coordinates, and I simply didn't draw my line very well, but it would have passed through this point. We read the coordinates, and we get a negative 1 and a positive 3. This is the solution to our system. This ordered pair will satisfy both the first and the second equation. Okay, what about part B? We now have a different system. The first one is in slope-intercept form, and so I take the y's by itself. That's how you recognize slope-intercept form. So I take the constant on the right side, the 3, has no variable. It's my y-intercept. So on my y-axis, I go up to y equal 3. I plot a point. And now I take my slope, m, it equals 2. And I can write that as a 2 over 1. 2 is my rise, 1 is my run. And so I go up 2 and right 1 to find a second point on the line. So up 2 over 1, or down 2 and left 1. And just keep in mind, whichever way you go, you want your points to fall in a straight line. Now we have to do a little bit of work on the second equation. We want to get the y by itself. So we add 4x to each side. They cancel on the left. We bring down the 2y that's still on the left. 4x and an 8 will not combine, and so we simply write them side by side, adding the 2. So 4x plus 8. And now we just go through the equation to get rid of the 2 in front of the y, and we divide by 2. This yields the slope-intercept form, which we need to graph the equation. 4 divided by 2 is 2, and then 8 divided by 2 is a 4. And if you compare this second equation with the original one, you can see that they have the same slope. This one had a slope of 2. The second equation has a slope of 2. And you also see that they have different y-intercepts. Alright, so if we plot our y-intercept for our second equation, we would put that at y equal 4, which is a little bit lower than that. That's y equal 5. I'll draw this one the color red. And so I found my y-intercept, I have my point, and now I start to apply my slope. I go up 2 over 1. And if we continue to apply that slope, we're simply never going to cross this other line. They just run alongside each other. And so if I drew them perfectly straight, okay, our sketch, these lines would never cross. They never intersect. They have the same slope, and so they're parallel. So in this case, this system has no solution. Graphically, there's no intersection, and so algebraically, there's no solution to this linear system of equations. So B is no solution to the system. Our last one on this page, we have one equation. It's already in slope-intercept form. We have the y-intercept 1 and the slope 1/2. So for this one, I'll sketch it in red. And so we have y equal 1. We plot that point on the y-axis. And then we have the slope 1 over 2. Which means that we go up 1 and over 2. And we can reapply that as many times as we want, as long as we start with a point on the line. And the only point that we knew in the beginning was its y-intercept. Okay, I'll plot this first one in green, but before we do that, we need to do a little bit of work on it and get the y by itself so that we can read the slope and the y-intercept. If we subtract x from both sides, that'll move the x away from the y. We cannot combine a 2 and an x, so we simply write out minus x minus 2. Now we divide each term by negative 2. And our slope becomes a positive 1/2 minus minus. And it's understood that there is a 1 in front of this x. And then a negative 2 divided by a negative 2 is a plus 1. And if you compare this equation with the red one, they're identical. And so we've already plotted a point at y equal 1. And then if we apply our slope of up 1 over 2, we fall on the same exact points as we plotted for the first equation. They're identical lines. And so they simply run over the top of one another. Well, which points do they share? An intersection is just a set of coordinates that two lines share the same x and y coordinate. Well, these two lines being identical would mean that they share every point. So there are infinitely many solutions. Not just to one equation, but the other. Now, it doesn't mean that any two x and y coordinates satisfy this system. It means that any point along either line will satisfy the system. Okay, so we could come up with several. We have the point, the y-intercept 0, 1. We have this other one 2, 2, and then any point in between that falls on the line. We have a third one, 1, 2, 3, 4, 3, and so on. Okay, this page is not telling us anything new about the procedure that we follow to find the solution of a linear system of equations graphically. It's just pointing out that these systems have names. Okay, the one that we graphed in the previous example, A, we would call consistent independent. It had only one solution. The two lines crossed in only one place. Alright, 2, if they're parallel, like the two lines that we graphed on the previous page for part B, then we call the system inconsistent. And then finally, if they are identical lines, 3, C, part C from the previous page, then we call the system consistent and dependent. Okay, so I suppose the easiest way to memorize this is if there's no solution, then the system's inconsistent. Okay, but the other two examples, 1 and 3, they do have solutions. So we call them consistent. But then the first one had only one solution, so it's independent. And then the third one had infinitely many, so we call it dependent. Okay, but if there's no solution, inconsistent. So for example 4, we simply want to name or label the type of system it is. Okay, so the system of equations is, if we look at the equations in the graph, well, the graph looks like these two lines are parallel, and if we want confirmation of that, we can look at the equations and compare the slopes. And for each line we have a slope of 5 over 3. 5 over 3. The coefficient of the x is 5 over 3. So these are parallel lines, and that would mean that this system is inconsistent, and therefore if they never intersect, then there is no solution. Okay, so same slope, different y-intercepts, inconsistent, no solution. Now if we look at these two lines, they have different slopes, and therefore they only cross in one place, one ordered pair. And so this is consistent because it does have a solution, but it's independent because there's one solution. And so we say unique solution, a unique, one solution. And from the graph we can read exactly which ordered pair that is. We get 1, 2 for x, and then a negative 1 for y. If you ever want to check and make sure you have the right coordinates, simply go back to your equations and try out the x and y pair for each one. Y is negative 1, x is a 2. Do the two sides work out to equal one another? 2 times 2 is 4, and if we subtract 5, we do get a negative 1, which matches the left. And now if we try the same ordered pair for the second line, we have a negative 1 equals 2 minus 3, and 2 minus 3 is a negative 1. And so the left hand side matches the right hand side for both line 1 and 2, so we have the correct coordinates. One intersection point, consistent, independent, a unique solution. One solution. And finally, doesn't look like there's two lines here, and that's simply because they overlap one another. You can see that we do have labels, L1 for line 1 and L2 for line 2. But the way the equations are arranged, they don't look identical. Okay, so if you want to double check this and make sure that they're just not really close, you could take the line 2. Line 1's already in slope-intercept form, so what we'll do is we'll put line 2 in the same form, and we'll compare it to the first one, which we think is going to be identical. So we get the y by itself, add 2x to both sides. We have a 2x minus 12. And now to get the y by itself, we divide by 3 each term in the equation. And we get a 2/3 for our slope, which matches the first line. And then negative 12 divided by 3 is negative 4, so it also matches the y-intercept. These are identical lines, and so we would say there is a solution. They do share some common points, so it is consistent, but it's dependent. And we say that there are infinitely many solutions because they overlap. They share all of the same ordered pairs. Alright, for this next example, what we're going to do is use our calculator to decide whether these ordered pairs satisfy line 1, line 2, both, or neither. Okay, so instead of grinding it out, calculating one side, plugging in the x and y, and seeing if it matches the left or right hand side, which may be quicker if we only had one point to check, one ordered pair, but we have several. And so an easier way is to use our calculator. But first, what we have to do is put these lines in slope-intercept form. So line 1, we add 7x to both sides. They cancel on the left. We can't add an x term with a number, so we write 7x plus 29 on the right. And now to get the y by itself, which is in essence slope-intercept form, we divide by negative 13, and we get a negative 7 over 13 for our slope, and a minus 29 over 13 for our y-intercept. For line 2, we do the same thing. We solve for y. X's cancel on the left, okay, after we subtract x from both sides to move it away from the y. And now we divide everything by negative 9. We get the y by itself. A minus divided by a minus is a positive 1/9. A minus divided by a minus for the slope or the y-intercept is also positive, and the fraction 15 over 9 can be reduced to a 5 over 3. So here are the two equations that we want to graph with our calculator, and we have to have them in slope-intercept form in order to graph them with our calculator. So we pull up our calculator, and since we want to graph something, we look below the display, and most of the buttons that we use to graph things with, or to graph things on our calculator, are below the display. We have our Y editor screen, Y equals button. We have the window, zoom to move closer to our line or our graph to get a better picture. Trace, which will place the cursor right on top of the line and run along the line as we move our cursor from left to right. And then graph. Okay, this button simply takes us to our coordinate system. We haven't entered any equations to graph, so if we hit the graph button, we see pretty much a blank coordinate system. It's our y-axis and our x-axis, and they give us a few tick marks on each one, but we're not going to get numbers. Alright, so what screen do we go to type in our equations? That would be this screen, the Y editor screen. And you can see that the y equals from our equation is already taken care of. And you may also notice that we have these numbers 1, 2, 3, 4, 5, 6, 7, and so on. These imply nothing mathematical in relation to our equations. They're simply labels, and they're differentiating one equation from the other. So this is equation 1, equation 2, equation 3, and so on. So what we'll do, since we're on line 1, we'll enter this equation. And we start with the negative 7 over 13. And what I'm going to do is I'm going to put parentheses around my slope. It's a fraction. I don't want the calculator to confuse the fact that the x is on the top, not with the 13. So parentheses, the minus sign that you want to use is the one that's grouped with the numerical buttons. And now we type in 13 for our denominator, and we place an x beside it, and notice that I close the parentheses before the x. And our y-intercept intercept is a negative 29. We can use the subtraction button since something came before the minus. And we divide that by 13 and we hit enter. And so the calculator has accepted our first equation. On line 2, we'll enter our second equation, which is 1 divided by 9, and then plus 5 over 3. Enter. Each time you need to hit enter. So we only use Y1 and Y2 from the Y editor screen. At this point, what we want to do, we don't want to look at the graph. We could if we wanted to, but we simply want to go to the table and check these ordered pairs. And the table's the easiest place to do that. So our first one is x equal 3, y equal 2. And so in the x column, we scroll down to x equal 3, and we look at the y coordinates of y1 and y2. This is line 1, this is line 2. Well, their y coordinates do not match, and so these two lines do not share the ordered pair 3, 2. However, the ordered pair of 3, 2 is on line 2. But since line 1 doesn't share it, it's not a solution to the system. What about our next one, negative 6, 1? We go up for negative 6 in our x-axis, and we go over and we look at the y coordinates, and they match. And they are the y coordinate that we were given for this ordered pair. We have negative 6, 1, and so this ordered pair satisfies both line 1 and line 2. The ordered pair is a solution to the system. Okay, what about our last ordered pair 6, negative 1? So we've sort of switched the negative over to the y coordinate, which is a different ordered pair. It's at a different location on the coordinate system. We go down our x column until we find x equals 6, and we compare the y coordinates for each line, and neither one of them are negative 1, and they don't match either. And so this ordered pair is not on either line, so it's definitely not a solution. So our last example of this chapter, example 6, we're given 2 more lines, our system, and so we want to take our calculator and clear out the previous one, get it ready for this new problem. And now we also have to take each line and do as we did before and put the equation in slope-intercept format at the y by itself. So line 1, we start out by subtracting 10x from each side. And to finally get the y by itself, we divide by 3. And this is where most of the work is involved with the problem. Once we get the slope-intercept form, then we can enter these into the calculator, and it will do the hard work for us. So line 2, we add 3x to both sides to get it closer to the slope-intercept form. Three x's cancel on the left, and we want to get rid of the -4 so that the y is by itself, and we divide by -4. They cancel out and they leave us with the slope-intercept form. We can write a -3/4 for our slope. We can simplify 14 over -4 and write it as a 7/2. And so here we are. This is what we need to enter into our calculator. And specifically, we enter the right hand side of each of these equations. And then we'll figure out what our solution is. And I'll show you another way in addition to the previous one. If you turn your calculator on and you start at the home screen, okay, if I turn my calculator back off and I turn it on, this first screen we go to, the home screen. It's just blank, cursor's in the top left. To graph equations, we start out with the y editor, so we hit y equals at the top on the left, just below the display. Y editor's blank, and so we'll enter our first equation, line 1, on that line, and the y equals part is already there, and we sort of ignore the 1, 2, and the 3. Alright, we have a -10, and so we want to use this negative that's grouped with the number keys. And I also want to put this fraction, my slope is a -10/3, it's a fraction, so I want to put that in parentheses so that the calculator doesn't misinterpret the x as being in the denominator. And here's my X button. Okay, there's a lot of other symbols on the X button along with it, but if you press this button, it's just going to give you an X. You would probably have to change some settings in your calculator if you wanted to use the tau, the theta, and so on. So if we press it, it gives us an X, and we can go on with our business and enter in the y-intercept for line 1. When you're finished, you simply hit enter, and the cursor jumps down to the second line. And the slope of this second line is also a fraction with a negative, so I'm just going to type parentheses -3, with the negative coming from this bottom button, not the subtraction symbol. Close the parentheses and then type the X for the equation. The last equation doesn't need to be, or the last numbers in the equation, the y-intercept, doesn't need to be in parentheses. Just type subtract 7/2 and hit enter again. And so at this point the calculator's accepted our two equations, and what we'll do is we'll look at the table to decide whether any of these ordered pairs are on line 1, 2, both, or neither. To go to the table, we have to hit the second key and then graph. You can see table is written in blue letters above the graph button, and so that just simply tells you that you have to hit the blue second button in order to access the table. Okay, once we're at the table, we have the X column, and then we have the Y values for equation 1, line 1, and line 2 in the third column. So the first one we want to check is an X equals a negative 1. So I go up, I find negative 1 in my X column, and I look over to the right, and our Y coordinate that we want is a 5, but we only have a 5 in the column for line 1, not line 2. So we would say this ordered pair is only on line 1. Okay, our second ordered pair, we want to find X equal negative 3 in our X table or column, and now we compare the Y values. Well, the Y value we were given for the ordered pair is a positive 3, and neither one of these lines have that Y value. We have a 11 and 2/3 for Y1 and a negative 1.25 for Y2. So this point is on neither line. So A or B, neither one of them was a solution to the system. So finally we check our last ordered pair. X is 2, okay, the first number in our ordered pair, and then we're given Y is negative 5, and each line in their columns has a negative 5 for Y, and so this point is on both lines. This is the solution to our system. Okay. In other words, this is where the two lines intersect, and so if we now simply hit the graph button without hitting the second key first, graph, okay, it always graphs the lines from top to bottom with respect to our Y editor. So this first one that it graphed, the steep slope, is line 1, and this other one is line 2. Okay, and you can definitely see that they intersect right there. Okay, one way, another way to check these coordinates is to simply type in, when you're in the graph mode, type in the number. You don't have to hit X equals, you don't have to hit X, you just simply want to hit your trace button, and then you want to enter the value for X for that particular ordered pair. So our first ordered pair is negative 1, 5. We hit the trace button, and then we hit negative 1, enter. Okay, we are on, you can see that the cursor is blinking, we are on line 1, and you can see that we get the Y value 5, which matches our ordered pair. So this point is only on line 1, and we obviously do not intersect at that point, and so that point is not on line 2. Okay, so we want to check the second ordered pair, so we hit trace, and then we type in our new Y, or I'm sorry, X value of negative 3 and hit enter again. And we can't even see the cursor. Okay, and we definitely do not get a Y value of positive 3. Okay, if you're in the trace mode and you want to switch lines, then you simply hit the arrow key up or down, and you can see that it swaps back and forth between Y2 and Y1. Okay, you can just hit down if you want to. If you hit down repeatedly, it's still going to jump back and forth between the two lines. Now, in the trace mode, we can check the second line for this ordered pair -3, 3. So we're in trace. We go ahead and type in -3, and you can see that x equals -3 pops up on the screen. We hit enter again, and we get the y value -1.25, which does not match the y value we were given with the ordered pair. So we've simply just confirmed that this ordered pair is not on either line. Now, we know that this is our solution. Okay, we can make the calculator tell us what the coordinates of that point are. The easiest way to do that is to hit second, calculate, scroll down the list until you hit intersect. It's going to ask you about the first curve. Just simply hit enter and then enter, and then it's going to ask you if you want it to guess, and you just hit enter for a third time, and then you'll see the cursor jump right on top of the intersection, and it actually gives us the coordinates of that point, and they match these coordinates that we found from the table to be our solution. X is 2, y is -5. And so I hope you got something out of the video. If you got any questions about it, feel free to come by my office. But that wraps up chapter 28. Thanks for watching.